Hi, I'm Daniel Balouek-Thomert, Research Associate at the Rutgers Discovery Informatics Institute at Rutgers University. In this segment, I will discuss stream data analytics and data-driven pipeline for IoT systems. The context of this seminar is to observe that we have an evolving service landscape. Not all of the work in distributed systems happen in the cloud, but we have a really complex set of resources that goes from the cloud to the edge of the network and involve Internet of Things sensors. I mean smart sensors, your watch, your car, video cameras. All of those elements are producing a huge amount of data that required processing in a timely manner. So somehow that's the first challenges we have to deal with when we discuss streaming analytics. I will give two numbers. The Cisco company estimate that there will be 500 billion devices in 2030. At the same time, Toyota described an amount of 10 exabytes of data per month flowing between autonomous vehicles and servers. So to be able to cope with that amount of information, we need to develop systems that are executed between the edge of the network when this data is produced and the core when this data will be processed. That data is meant to be complex. It's in different shape, a lot of different type, but also needs to be processed according to different feature. Temporal feature, if the data is not processed in due time, it will probably lose its value. Spatial context, notably in the context of moving sensors, but also context-aware processing. Data acquired in one situation might not be relevant when it's crossed in the wrong domain-specific application. So dealing with streaming analytics in our time means coping with an evolving service landscape, but also the huge variety of IoT sensors and applications. At this point, we discuss about data-driven pipeline and the ability to be able to transform and reuse that data is mainly based on four different elements. The first one is the acquisition and being able to collect the data while preserving features such as privacy, which is really important in our time. Then we go on to the processing of the information, namely complex workflows, functions that could come from different entities, different resources, to be able to extract valuable information. The third part is about storage and how to ensure that data is not lost, properly replicated, and also in the proper place. And finally, actuation, which is the way to get feedback from the three previous steps. If you think about it, we have video analytics from a camera. Based on the data that is analyzed at the current time, we might want to switch the orientation of the camera. This is one of the numerous examples that says to us that it's a continuous process. We get the data, we process it, store it, and get the best feedback out of it. So to be able to program streaming analytics, we really have a need to be able to express what, where, and when to compute the data, especially when considering issues such as low latency, privacy, location, and content-aware feature. Doing an automatic orchestration and programming reactive behavior out of here is the challenge of this seminar. In this segment, I will highlight two different challenges to be able to support advanced analytic and sensor application in this continuum of services. The first one is about complexity and the ability to deal with huge variety in sensor data, communicating hardware, and computing resources. The second one is about distribution. It's not only about the data, but the ability to collect from billions of devices that are spread across large geographic areas or even with network constraint capabilities. Regarding the complexity of elements, we can think about sensors that are power constrained, meaning that the better the algorithm and the mechanic are, the better the battery and the duration of the device will be. So there is a need to do a good job at dealing with these resources, but also managing their availability, knowing that the edge of the resources can be unreliable, can go offline, and also have capacity limit. We are used to deal with a well-provisioned data centers, but now we are talking about constrained resource devices, small computing unit that could fit on a drone, for example, but also need to be properly managed. So we want to have a programming mechanism that could help us deal with the different capabilities of devices. One of the solutions we propose in our research at the Rutgers Discovery Informatics Institute is to reason on attributes rather than the name or specific sensors that are deployed in the wild. One programmer might prefer to do a query that says, I would like to retrieve data from all the video cameras that are from a certain quality, which allow to reason without actually knowing the underlying hardware. By using a common low-level interface for data collection and aggregation, when we describe each of the resources based on its attributes, we're allowing the definition of new operators for search, query, and storage that are describing the inner property of the data to be exchanged. In this example, a profile consists of keywords or tuples, wildcard ranges that are describing the data product and can be updated or controlled at runtime without synchronization, and more importantly, without alerting the whole federation of resources. The second challenge is the distribution of the resources and how to organize all of those computing elements according to their physical location and application constraint. In this context, we use principles from the peer-to-peer community to enable automated placement of storage and processing of sensor data between the edge of the network and the core of the network. There is multiple criteria that can be used to do so: performance, energy consumption, privacy. We're trying to use all of those elements in a programming model so that developers can enable streaming analytics with the understanding of all those resources. I will finish this segment by describing what can be achieved once we deal with the complexity and the distribution of the resources. Using a rule-based system engine to enable operation behavior, we can enable the programmer to specify what, where, and when to compute data using data quality rules such as approximation, accuracy, which will look at the inner properties of the data and be able to create content-driven rules, an if-then system, if you prefer, when data can be used at the edge of the core of the network and trigger more computation if needed. Those behavior can be applied to disaster recovery management, video analytics, and a lot of other fields such as precision medicine to be able to react to the content of the data and produce reactive software. Thank you.